In this video, we're going to see what happens as we heat up a substance. So we're going to be adding energy and seeing what happens to that substance. To see what happens, we're going to need to know some basic terms in order to understand what's happening along the way. So we're going to start with some terminology and then we'll do a graph to show you what happens as we heat up a substance. There are 5 physical constants that you'll need to know what the terms mean that are used while heating any substance. You may not use all of them in every question, but you will use one or more of these in each question. Of these 5, there are 2 different types. The first type are the ones that say specific heat. A specific heat is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. These specific heats are specific to the type of compound you have. Is it a solid? Then it's the specific heat of a solid. If it's a liquid, it's the specific heat of a liquid. And if it's a gas, it'll be the specific heat of that gas. And that is how much energy it takes to raise 1 gram of either the solid, the liquid, or the gas by exactly 1 degree Celsius. In this case, there is no change of state. That means if it's a solid, it stays a solid. If it's a liquid, it stays a liquid. And if it's a gas, it stays as a gas. The other type are the ones that are called the heat of. So you'll see one is called heat of fusion and the other one is heat of vaporization. I'm going to start with the heat of vaporization because it's a more obvious statement. Here, the heat of vaporization is the energy required to change 1 gram of any substance from the liquid state to the gaseous state without a change in temperature. The temperature will remain the same. Notice that in the specific heats, the temperature was changing by 1 degree Celsius. In the heats of, we don't change the temperature at all, but we do change the state. For the heat of fusion, it's kind of the same statement. In this case, it's the energy required to change 1 gram of a substance from the solid to the liquid, what we would call melting, without a change in temperature. You may have noticed that in chemistry we use lots of abbreviations. Well, we have abbreviations for these also. So every time you see specific heat, the official abbreviation is the letter C. And that just means it's a constant because this is a constant for something. And then if we want to indicate that it's a solid, we're just going to put an S. If it's a liquid, we'll put an L. And if it's a gas, we'll put a G. I'm going to make it a little bit easier for you, and I'm not going to use the letter C. I'm going to use the letters SH for specific heat. So that as I'm going through the rest of these notes, you'll see me write SHS for the solid, SHL for the liquid, and SHG for the gas. So these are the specific heats of the solid, the liquid, or the gas. The abbreviation that's used for heats of is a delta H. The delta just means change, so it's the change of heat. And then we'll put an F for fusion and a V for vaporization. Or sometimes I put FUS and VAP, but you have the basic idea that the delta H means heat of. So let's look a little bit at the differences between the specific heats and the heats of. In the specific heat, you'll notice, of course, we have the abbreviation C or SH, whereas the heat of is delta H. In the specific heat, you'll notice that it always says a solid, a liquid, or a gas. That is specifying what state, what physical state we're looking at. So we can look at just the solid, just the liquid, or just the gas. And you will have a different specific heat for each of those. They are not going to be the same. When we look at the heat of, it doesn't say whether it's a solid, liquid, or gas. And that's because it's changing the state from a solid to a liquid or a liquid to a gas, or even vice versa. It can be from a gas to a liquid, which is our condensation, or from a liquid to a solid, which would be, of course, freezing. So we can see any of those. There's still going to be the heat of for those things. But what's really important to notice that is different between the specific heat and the heat of constants is how one of them has something that changes and the other one is constant. And it really shifts from one to the other. So when we look at specific heat, we see that the temperature is changing, but the physical state stays the same. And how do you know what state it is? By looking at the name of the constant. So it's either a solid, a liquid, or gas, and it stays as a solid, liquid, or gas. When we look at the heat of, we see that the temperature stays the same, but that the physical state changes. So it changes from a solid to a liquid or a liquid to a gas or vice versa. As I stated earlier, sometimes you'll be using only one, but sometimes you'll be using more than one of these specific heats and heats of. How do you know what to use and when to use it? Let's look at that next. This next section is not in your lecture notes, so you may want to get an extra piece of paper for it. Here we have a list of different things being heated or cooled. And we're going to categorize each of them as either a specific heat type of constant should be used or a heat of should be used, and then after that we'll decide whether it's the solid, liquid, or gas, or fusion or vaporization. So let's go through the first couple of them together, and then I'll leave the rest of them for you to do. So number 1, a solid is heated from 70 degrees to 80 degrees Celsius. So notice that we're telling us it's a solid, and then it's saying it's changing the temperature. If it's doing a temperature change, 70 degrees to 80 degrees, we're going to be looking at a specific heat. Now this specifically says solid, so that means we're looking at the specific heat of a solid. That's what we would use for this portion. Notice that it's 70 degrees to 80 degrees Celsius and it says it's a solid. Do you think this is water? No, it's not, because water would be melted at 70 degrees Celsius. So this is some other substance. Notice that these constants can be for any substance. They all have different specific heats and heats of, and they're very specific to that chemical. Okay, let's try the second one. Number 2, a liquid is boiled at 145 degrees Celsius. Again, this is not water, right? Because water would be completely boiled at 100 degrees Celsius. So is this a specific heat kind of question or a heat of? Notice that it says it is boiled at 145 degrees Celsius. So that is not changing temperature. What it will be doing is changing states as it's boiling, so that tells us it's turning into a gas. So this should be a heat of, because it's the same temperature, but we're changing it to a gas, so that'll be a heat of vaporization. Now I'd like you to try the rest of them, so go ahead and pause your video, read through each one, and decide what type of constant would you use for each of these problems. All right, I hope you were able to get those. Number 3. We have a gas is heated from 23 degrees Celsius to 59 degrees Celsius. Here we're seeing a temperature change. That tells us it's a specific heat. And then the statement says it's a gas, so that means it's going to be a specific heat of a gas. And number 4, it says a liquid freezes at 283 degrees Celsius. Now notice it gives us a temperature, but it's not changing temperature. And it says it was a liquid, but it's freezing. In this case, it's being cooled rather than heated. Doesn't matter. We're going to be looking at the freezing point or melting point. Remember, those are the same temperature. And this liquid freezes at 283 degrees Celsius. Again, this is definitely not water. But we see that this is going to be a heat of fusion that we would use. But in this case, it's going to be cooling rather than heating. And the main difference would be, rather than how much heat is being absorbed, it's how much heat is released as it's being cooled. Now number 5, we have the gas condenses at negative 28 degrees Celsius. So what do we see here? We have a gas, it's condensing, and it gives us only one temperature. That tells us that it's a heat of, because there's only one temperature. It's saying it's condensing, which is a change of state. Condensation is when it goes from a gas to a liquid. So that one is going to be a vaporization. And again, this appears to be one of the ones where it's cooling rather than heating. And our last one, number 6, a liquid is heated from 187 degrees Celsius to 325 degrees Celsius. We notice we have a change in temperature, so that's going to be a specific heat. And it tells us that it's a liquid, so that'll be the specific heat of a liquid. Now let's see what happens as we heat a solid and we turn it into a liquid and then turn it into a gas. We're going to be heating this substance up, and we're going to show that change of state in this change of state diagram, also known as a heating curve. In this specific case, I'm going to use an example of water because most people know the melting point and the boiling point of water. But it could be for any substance. It does not have to be for water. We're just going to use that as our example. For this graph then, what we can see are the tick marks on the y-axis are going to be 10 degrees each. And I'm going to start with the block of ice, that would be a solid, at negative 20 degrees Celsius. And that's going to be on the left-hand side. We'll put a negative 20. And then you can go up from there, negative 10, then 0, 10, 20, 30, 40. 50, 60, 70, 80, 90, 100, 110, 120, and those are all on the y-axis. On the x-axis, we're going to be adding energy. Now, I'm not going to talk about the actual amount of energy because that will vary dependent upon how much substance I have. So if I have a larger mass, it's going to take more energy. We're just going to call it energy added, and you're going to compare which of these processes takes the most energy. So an increase in energy is going to be going further on the horizontal line. As we go up the vertical column, that's telling us that the temperature is increasing. For my energy added, I like to draw a little candle here, and that's just saying that I'm heating it up. And as we're going across here, we're just continuing to have that heat added to it. This would be an example of heating something up on your burner at home. As you add heat, what's going to happen to it? So here we're going to start with an ice cube, and it's going to be at, and again, we're using water as our example, an ice cube at negative 20 degrees Celsius. That's right here at the very bottom. We've added no energy at this point. It's just sitting there. And then as it starts to warm up, we're going to add some energy to it. And the first thing it does is it starts to get higher and higher in temperature. So we're seeing a temperature change, and that is for a solid. So this is telling us temperature change. That means we're going to be using a specific heat at that point, and we know it's going to be the specific heat of the solid. Then at this point, it starts to go flat. Now what's going flat here is the temperature. That means that the temperature is no longer changing. That means something else has to be happening. We're adding energy to it. As we add energy, we're going to weaken the bonds that are holding those water molecules together to form it into a solid. Now they're able to slip past each other, and they start to become a liquid. Now, does it happen all at once? No. If you've ever watched ice melt in your glass, you'll notice that parts of it start to melt, usually the outside parts, and then it goes in further and further. So it doesn't all immediately change into liquid water as an instantaneous thing. That's because energy has to continually be added to it. But while that energy is adding, notice that we keep the same temperature. So that if you find a river and you find ice on the edges of that river, if you see there's ice and river, you know that that river is going to be at 0 degrees Celsius because that is the melting point or freezing point of water. Notice that we have a horizontal line here. Whenever you have a horizontal line, that is when there is a change of state and we are no longer changing the temperature. So as we start to heat this up, we start melting more and more of the water. What is present? We're going to have both the solid and the liquid present at this point because we're changing it from a solid to a liquid. And we're going to go from all solid to a little bit of liquid, more and more and more liquid forms, and less solid will be present until we get to this point. At this point, we've run out of solid and it is now all liquid. So which constant would you use for that? Notice that we're not changing temperature. That means it's going to be one of the heats of, and we're going from a solid to a liquid, so that should be a heat of fusion. Once we're at that end point, we've now melted all of the ice, and now the water, the liquid water, can start to rise in temperature. And so you'll see it rising back up here. Notice that it doesn't go instantaneously up to boiling. We know that that happens in life. It doesn't instantaneously begin to boil. It takes a while for it to warm up. So we're going to increase the temperature, and we're going to increase and increase. Notice that this is all liquid all the way up till it hits this point. The temperature has raised, but the state has stayed the same. It has stayed as a liquid. So what constant to use for that point? Notice that the temperature is changing, so it's going to be a specific heat. And at this point, we're looking at the liquid, so it will be the specific heat of the liquid. And what happens next? Once it hits this corner, it is now going to start converting it into a gas. And notice that it's flat again. That's telling us there's a change of state occurring and we're no longer changing the temperature. This is now your heat of. And which heat are we looking at? We're looking at the heat of vaporization because we're turning it from a liquid to a gas. Notice that at this point in the curve, a lot of energy is being added, but there's no temperature change. So what's actually happening? What's happening to the chemical? What you should see is that we're turning it from a liquid to a gas, and that takes a lot of energy. And what's happening on the submicroscopic level is that those intermolecular bonds, the things that are holding the water together, are actually being broken. So earlier when we saw it was melting, they were being weakened and they were somewhat breaking, but not completely. What we see here is that they have to completely break away so that the gas can escape from the liquid. And for that to happen, we have to break those interparticle forces. Notice this doesn't damage the H bonded to the oxygen bonded to the other H. So the H2O is still going to be the same chemical, but we're going to be breaking it apart from other H2Os. So each of the H2Os will be separated from each other, and that takes a lot of energy. And that's because in the case of water, there's a very strong bond holding those particles together. Now all through this section, we're going to have both the liquid and the gas present. We're going to have more and more gas as we get further and further across. So we'll start with almost all liquid at the start, and as we go across, we're going to make more and more of it turn into a gas until we get to this end point where it is now all a gas. And which constant will you use for that section? Well, when we're doing these, when we're changing the physical state, you're going to be using a heat of. This is going from a liquid to a gas, so this should be the heat of vaporization. Now that we hit this end point, we've turned it all into a gas, and now the temperature rises again. As the temperature rises, we're going to use another constant. In this case, it's all gas, so this is going to be a specific heat of the gas. Now, does that make sense that you can heat up water above 100 degrees Celsius? Well, you certainly can heat the steam above 100 degrees Celsius. It takes a little bit of work. We don't normally do it because there's no reason for us to do it, but do you know that you can heat the air? So if you think about the air, this morning it was a little bit cool. As the day progressed, as the sun beat down on the air, you'll notice that the temperature rose, and then later it cooled off. So we can change the temperature of the gases. We just don't normally do it with water because we don't have a good way to collect it and heat it. So let's talk about some types of questions you might see in this class related to a heating curve. So on this heating curve, we have a different chemical. This is not water, and I know that because of the temperatures that are here. And we're going to see that it starts at 70 degrees and it goes up to 350 degrees, and each of these is a 20-degree line. Don't worry too much about the numbers. We're not going to worry about them in any calculations in this course. And on the x-axis, we see the energy added, and that is your going from 0 to 950. It doesn't say what the units are. The usual units for these are joules or calories, and you've probably heard of calories before, and that's the amount of energy required here. And so let's just look at this curve. Well, we're not going to do any calculations in this course. I want to give you some examples of the types of questions you might see. Our first question is, what would be the melting point of this substance? And all you're going to do is you're going to look for this first flat line. The lower one is where your melting point is. And you'll see that that's area B, and we can read the actual melting point is 110 degrees Celsius. And recall that the melting point is also going to be the same as the freezing point. And then we can ask the boiling point, and that's going to be the other one that's kind of a flat line up here, and that's letter D. And if we read all the way across, we read over to here, and we can see that that's about 310 degrees Celsius. And of course, this would be the condensation point in a cooling curve. So we can know the boiling point and the melting point just by looking at this heating curve. And of course, you would see the same thing in a cooling curve. Another set of questions that might be asked are, what is happening in each area? So if we start over here with letter A, what's happening at that point is the temperature is changing, and we know that this is a solid because we're at the very bottom. So in area A, we are heating a solid. In area B, we've got a flat area here, and that is where we're going to be changing a solid into a liquid. So we might say that thing that is occurring is that it is melting. And in area C, we see that the temperature is rising again, so that means that we are heating something up, and this is going to be our liquid, so we're going to be heating a liquid in area C. In area D, we're going to be changing things from a liquid into a gas, and we call that term boiling. So going from a liquid to a gas is boiling. When we reach area E, we see that we're now all gas, And so this is going to be heating a gas, which is an increase in temperature. So we're just heating up the gas, increasing the temperature of the gas. Another set of questions that you might see is, what physical states do you see present in each area of this curve? So at the very bottom, we should see only the solid. In all of area B, we're going to have a combination of a solid and a liquid. We're going to have both of them present in area B. And that's because that's where it's melting. It's changing from one to the other. There are different proportions. So early in the graph, we're going to see that we have mostly solid with a little bit of liquid. And towards the end, we're going to see that we have mostly liquid with a little bit of solid. It's changing from one step to the next. Then as we go up, we're going to see that we have only the liquid present. So whenever you see that rise in temperature, that means you have only one state. But then when you see it go flat across, you know that you should have two different states. So when you get to letter D, you should see that that is going to be both the liquid and the gas. And how do I know if it's the melting or the boiling? We know this because of the position on the curve. So it depends on what you start with, of course. But in this case, area D is going to be having a liquid and a gas. And again, we're going to have mostly liquid at the start of this line. And as we go across, we're going to get more and more gas until we get to area E, which is all 100% gas. And another question set that we might ask is, what constant would I use to calculate each of these areas, how much energy is being added? And so for area A, the constant we would use, because it's just a solid and we see the temperatures rising, that's going to be a specific heat, and it's going to be of the solid. And now let's look at area B. Here we see we have the solid turning into a liquid. We know that is melting. That is not changing temperature, so this is going to be a heat of, and in this case it's going to be the heat of fusion. Area C, we see a rise in temperature again, so that's going to be a specific heat. At that point we have only liquid present, so it's going to be the specific heat of a liquid. In area D, again, when we go flat, we're not changing temperature. That means this is a heat of. Up here we have a liquid turning into a gas, so this is going to be the heat of vaporization. And in area E, we have all gas, and we're seeing the temperature rise, and this one is going to be our specific heat of a gas. Another type of question you might see are some questions that ask you to compare different areas of the graph. So we might see a question which asks, which area of the graph has the largest change in temperature? And of course, this is going to be looking at the y-axis, which one changes the most in the y direction. And hopefully you can see that's area C, and we know that that is going to be heating the liquid. And which one takes the most energy? The one that takes the most energy is the one that takes the most going across in the horizontal direction, and that's going to be letter D, which we saw was the boiling point. So now let's look at heating and cooling curves and see how they differ or how they're similar. What we're going to see on the left-hand side, we have a heating curve, and on the right-hand side, we have a cooling curve. The first thing you might notice is that on the heating curve, the temperature is increasing. That shouldn't be surprising to you. Whereas on the cooling curve, the temperature is decreasing. Next thing we're going to notice is on the x-axis, we're going to know that we are increasing the heat, adding heat energy in a heating curve. In a cooling curve, we're going to be removing the heat. So we're going to call this a cooling curve because we're taking the heat away, and that means that we're looking at the amount of heat released as we go across this curve. Let's follow quickly what happens in the heating curve. We're going to be starting with a solid. It is going to be heated, which means the temperature will rise. Then the solid starts to melt, turning into a liquid, and then that liquid starts to be heated, and that means its temperature rises until it hits to the boiling point, at which point the liquid turns into a gas, and we say that the liquid boils until all of the liquid turns into a gas, at which point the heat is added to the gas and the temperature of the gas increases. Notice that in the cooling curve, we're starting with a gas, which has a lot of energy, and it starts to cool down, so the temperature drops until it hits the condensation point, which is also known as the boiling point. The condensation point, it starts to turn from a gas into a liquid, and it goes across where the gas turns into a liquid until we hit the point where all we have is liquid present. At that point, the liquid starts to cool, and we see that the temperature drops. And again, we're releasing energy as that temperature drops until we get to the point that the liquid turns into a solid, which we call the freezing point in this case because we're going from a liquid to a solid. And then we're going to go over here until we hit the end of that. When all of it has solidified, it is now only solid, and the solid starts to cool down, so the temperature drops. On this cooling curve, you should be able to find the freezing point, which we find right here. You should be able to find the condensation point, again, which is in this region. And you should be able to tell me which of these processes shows the largest change in temperature. And here we see that is going to be the gas decreasing in temperature, so that one has the largest change. And finally, which one has the largest change in energy? Well, for this graphic, it's a little bit harder to tell, but it appears that this purple region is slightly longer in the horizontal direction. And so I would say that in this case, it is the condensation that is releasing the most energy, although the one with the gas is fairly close, and so is the melting. Those are fairly similar in size. We can clearly see that cooling the liquid and cooling the solid releases less energy. But the rest of them are fairly close. On your exam, they will be definitely a significant difference so that you can easily tell which one releases the most energy. Here are some sample problems to give you some idea of the kinds of questions you might see. Go ahead and stop your video for the moment, and when you're done, come back and we'll go through the answers. Okay, now we're back. First, number 1, is this a heating curve or a cooling curve? As you can see, the temperature is going down, so this would be a cooling curve. Number 2, what is occurring in area E? So if we look at this, we're starting with our gas, and we're going all the way down to letter E, which is at the bottom here. That's a solid, and we see that it is cooling, so we're cooling the solid. Number 3, what is the boiling point of this compound? The boiling point is up here where we see both the gas and the liquid, and that, if we're going to reach straight across, it looks like it's really close to 100 degrees Celsius. What about the freezing point? That's going to be down here in area D, again where we see the flat area, and it is the lower one, and that one looks like it's 0 degrees Celsius. This may be water. Might not be, but that is the temperatures that we normally see for water, so I wouldn't be too surprised if it is water. And number 5, which area of the curve shows the largest change in temperature? So we're looking to see in the y-axis which one changes the most, and that is clearly letter C. So letter C is going to be the one that has the largest change in temperature, and that is our liquid cooling. Number 6, which area of the curve shows the largest change in energy? And to answer that, we're going to look at which one has the largest change in the x direction. And we can see clearly that letter B has the largest change in the x direction, or the largest change in energy. This is actually fairly interesting because when you get a steam burn, what's really burning is that you're changing the steam, the gas form, into the liquid form, and that releases so much energy. That's what actually burns your skin. So what do you see when you're making some spaghetti and you see the steam coming off? What we see steam. That steam that you see is actually not in the gas form because you can actually see the particles. That is a very separated, but it's still a liquid form, and it's very hot, but it is not the same as actual steam. If it were steam, you would not see those particles until they condensed into a liquid, and that change from the gas phase to the liquid phase is what releases so much energy. So a steam burn releases a huge amount of energy. The amount of energy released to turn that liquid into a cooler liquid down to your room temperature, let's say, is not nearly as much as the amount of energy it takes to get it from a gas to a liquid. And so what we see is that the steam burn, when you get a steam burn, it is all from the condensation of the liquid. All right, let's move on. Number 7, what are the physical state or states of the compound in area A? In area A, we have just the gas present, so we should have just gas. What about for area D? So number 8, what is or are the physical state or states of the compound in area D? Here we're seeing one of those flat lines that's telling us that we have 2 different physical states. In this case, we're on the lower one, and so this will be both the solid and the liquid because we're seeing it freeze at that point. And number 9, what temperature do you think the system will be if there is both a solid and a liquid present at the same time? Well, as we saw, in area D, we have both the solid and the liquid present. And so in this case, we're going to read across, we're going to see that the freezing point is 0 degrees Celsius, so this will be 0 degrees Celsius. As I mentioned before, if you're in a river and you see both the solid and the liquid present, you know that that river is at 0 degrees Celsius. It's a mighty cold bath if you go in there. And number 10, what constant should you use for area C? Area C, we can see, has a change in temperature, so that tells us that it will definitely be a specific heat. And in this case, we see that we have a liquid, so this should be the specific heat of a liquid. And finally, number 11, what constant should you use for area B? Area B is flat, going horizontal. We don't see a change in temperature, so that means this is going to be a heat of. Is this heat of vaporization or heat of fusion? Well, here we see both the gas and the liquid are present, so we'll be using the heat of vaporization. I hope that helps to give you some idea of the types of things we can do. In more advanced classes, they'll actually have you do some calculations, but in this class, we're just going to ask you these types of questions.